In this video, we're going to discuss the concept of the mole. We're going to start by discussing what is a mole. Then we're going to talk about why we use the concept of the mole. We'll talk about how much or how large a mole is. And finally, we'll look at how to use the mole in some calculations, paying careful attention to the units associated with a mole. So let's start off. What is a mole? Well, the mole, which is sometimes abbreviated as MOL, is the SI base unit, so the standard unit in science, used to measure the amount of a substance. Now, just to be clear, use the mole when we're talking about the amount of something, not the mass of something. For example, if we wanted to know how many atoms are in a sample, we would measure the number of atoms as moles. However, the mole would not be used to measure how much the sample weighs. There we would use grams or micrograms, something like that. Well, the mole is the unit of amount, and it turns out that 1 mole of something, 1 mole of particles, is equal to 6.022 times 10 to the 23rd particles. So let's try to define that a little bit more clearly. The mole is a unit of amount. There are other units of amount that we're very familiar with. A dozen is a unit of amount equal to 12. A pair is equal to 2 of something. A case of particles is equal to 24 particles. A case of soda cans is equal to 24 cans. So these are common units of amount, and just like the mole, a mole of something is equal to 6.022 times 10 to the 23rd. So for example, if you had 1 dozen eggs, you have 12 eggs. If you have a mole of eggs, you have 6.022 times 10 to the 23rd eggs. If you had a case of soda, you would have 12 soda cans. A mole of soda, you have 6.022 times 10 to the 23rd soda cans. So the mole can sometimes be abstract. It's good to be able to relate it to something like a dozen. It's simply a unit of amount. We'll talk about why we use that in just a little bit. Now, a mole of something, we generally don't use the mole when we're talking about eggs or soda cans. We use it when we're talking about things related to chemistry. So if you had a mole of atoms, you have 6.022 times 10 to the 23rd atoms. It doesn't matter if it's carbon, sodium, gold, it's a fixed number. So that's how many of those atoms you have. Same thing with molecules. When we're dealing with a mole of any type of molecules, carbon dioxide or water, we have 6.022 times 10 to the 23rd of that molecule. Or ionic compounds. A mole of any ionic compound is equal to 6.022 times 10 to the 23rd formula units of that compound. Remember, we use formula units to indicate the smallest portion of an ionic compound. So we could have a mole of electrons, and that would be 6.022 times 10 to the 23rd electrons. Now, like all units, the mole has to be based on something reproducible. We have to have some standard. Where did that number come from? Why did we choose 6.022 times 10 to the 23rd? Well, the mole is defined as the number of carbon atoms in exactly 12 grams of pure carbon-12. So that's where that number came from. That's the definition of a mole. Put another way, it has been established that 12 grams of carbon-12, so if you have exactly 12 grams of carbon-12 atoms, you have exactly 6.022 times 10 to the 23rd carbon atoms. So 1 mole of anything, 1 mole of carbon-12 is equal to 6.022 times 10 to the 23rd carbon-12 atoms. But again, we can use the mole to measure anything: pencils, soda cans, atoms, molecules, formula units. Now, 6.022 times 10 to the 23rd is often a mouthful to say, so this number is often called Avogadro's number, abbreviated as Na, after the scientist Avogadro, who helped discover or develop the concept of the mole. So why do we use this concept of a mole in chemistry? Well, chemists need a convenient method for counting accurately the number of atoms, molecules, formula units in a sample of a substance. And of course, as you know, molecules, atoms, formula units, these are extremely small things. So there are so many atoms, let's say, so many atoms in even the smallest sample that it's really impossible or impractical to try to count them. So therefore, instead of trying to count individual atoms or say how many individual atoms we have, it's more convenient to count or work with atoms in large groups called moles rather than the individual things. So it's, for example, let's say we had a sample of sulfur here. We could say, oh, we have 1.024 times 10 to the 24th sulfur atoms, for example. Or we could say that we have 2 moles of sulfur. These are the same thing. These two are equivalent, as we'll see later, but it's easier to deal with these atoms in large groups because individual atoms, there's just so many of them that it becomes a bit cumbersome to deal with. So a mole is just a group of atoms or molecules, and it's more convenient to work with them in large groups. So the mole is a large group of something. How big? How much is a mole? Well, a mole, 6.022 times 10 to the 23rd, is a huge number, 602 sextillion of something. For example, let's put that in perspective if we can. If we had a mole of basketballs, that would be enough basketballs to make a planet the size of Earth out of those basketballs. If we had a mole of marbles, that would be enough marbles to cover the entire Earth to a depth of 50 miles. So a mole is a huge number. It's almost unfathomably large. Well, why do we use such a large number? Well, again, because we're dealing with very tiny things. What if we had a mole of water molecules? How much space would that take up? Well, it would only take up about 18 milliliters or 4 teaspoons. So if we had 6.022 times 10 to the 23rd water molecules, 1 mole, it would only cover about 18 milliliters or about 4 tablespoons. It goes to show you just how tiny molecules are. Well, what if we had a mole of copper atoms? That would be enough to make about 22 pennies, assuming pennies are still made out of copper. In other words, if you had 6.022 times 10 to the 23rd copper atoms, or 1 mole, you could only make about 22 copper pennies. Again, just goes to show you just how tiny atoms are and why we need such a huge number when we're talking about atoms or molecules. Well, we need to use the mole in calculations. That's going to be a very important part of chemistry. So when performing calculations, we want to use dimensional analysis whenever possible. And when we use dimensional analysis, we need to write conversion factors. So for example, a mole, the equality, we've talked about this before, of course, a mole is equal to 6.022 times 10 to the 23rd particles, where a particle can be anything. So we could write this, 1 mole of something, we could write it as a conversion factor. We could write it as 6.022 times 10 to the 23rd particles over 1 mole, or if we needed, we could reverse it and put the 1 mole on top and Avogadro's number on the bottom. Both of these are correct ways of writing the mole as a conversion factor. But we need to be very careful with what units we use when we're talking about the mole. We have to be very specific. So what units should we associate with the mole? Could be anything. Well, let's try a problem. Express each of the following as a conversion factor, kind of like I showed you just in the last slide. Express each of these as a conversion factor and write the correct units when you express it as a conversion factor. Pause the video, give it a try, and see what you come up with. Okay. So 1 mole of copper. Well, we could write it either way. Avogadro's number of atoms, we would want copper atoms here, is equal to 1 mole of copper. Again, because copper is an atom. We could write it either way would be correct. CH4, methane, this is not an atom, so we can't use the unit atom. This is a molecule. So we would have Avogadro's number of molecules over 1 mole of CH4, or we could write it in reverse. 1 mole of calcium chloride. Calcium chloride, is an ionic compound, of course, and so we would want to use the units, formula units, when we talk about ionic compounds. So we could write the conversion factors either way, paying careful attention that we have the correct units, not atoms or molecules here. And finally, iron 2 plus. Well, iron 2 plus is a cation, so we could either write Avogadro's number of cations or ions over 1 mole of iron 2 plus, and we could write it with Avogadro's number on top or bottom. Now let's practice a couple of problems where we use conversion factors. How many copper atoms are in 0.50 moles of copper? Again, use dimensional analysis, show your work, watch your units, and solve this problem. So we start out with what we're given. We're given that we have 0.50 moles of copper. How many copper atoms do we have? Well, we want to use a conversion factor where we have moles of copper on the bottom and Avogadro's number of copper atoms on top. We put the moles on the bottom so they cancel, atoms on top, and we multiply. Here we have 2 sig figs. This is not an exact number. This has 4 sig figs, so my answer would have 2, and we'd have 3.0 times 10 to the 23rd copper atoms. Again, be sure that you don't leave off the units when you're writing your conversion factors. Let's try one more. 2.50 to the 20 times 10 to the 24th molecules of carbon dioxide is equivalent to how many moles of carbon dioxide? Again, pause the video, use dimensional analysis, show your units, and solve the problem. So we start out with what we're given. We have 2.50 times 10 to the 24th carbon dioxide molecules. We want to use a conversion factor where we have molecules on the bottom. 1 mole of carbon dioxide is equivalent to 6.022 times 10 to the 23rd carbon dioxide molecules. We want the molecules on the bottom, moles on the top, because that's what we're solving for. And we divide in this case, solving for 3 sig figs, we get 4.15 times 4.15 moles of carbon dioxide. So appreciate what we said here. If you have 2.50 times 10 to the 24th carbon dioxide molecules, that is equivalent to 4.15 moles. These are the same thing, exactly the same thing. We're just stating it a different way. Again, because 4.15 moles is often easier to work with than saying we had 2.50 times 10 to the 24th carbon dioxide molecules. So appreciate what a mole is and how to use dimensional analysis to solve problems involving the mole.